So now that we've talked about the life cycle of high and low mass stars, now we're going to start talking about stellar remnants. These are the things that the stars leave behind after they've died. But before we get to that, here is our third lecture quiz question. What is the final stage of a low mass star? A. White dwarf, B. Brown dwarf, C. Yellow dwarf, or D. Red dwarf? Go ahead and think about it and we'll discuss in just a bit. Alright, so what is the final stage of a low mass star? The correct answer is A. White dwarf. A brown dwarf is something that was close to having enough mass to begin fusion but didn't actually get there. Yellow dwarf and red dwarf, those are both types of main sequence stars. A is the only thing that is a stellar remnant. So low mass stars do not reach the pressure or temperature necessary to begin carbon and oxygen fusion, as we've mentioned previously. Now eventually all of the outer layers of the star are going to be blown off, leaving just the core behind. That core, which is now going to be composed of carbon and oxygen, this is the white dwarf. Now in this image, that's right here. Okay, this is actually a companion to the bigger star right there. Now at the point that we actually see the white dwarf, there's been no ongoing fusion in the core for a very long time. There may have still been some shell fusion in the star for a while, but there's been no fusion in the core for a very long time. All white dwarfs are held up against the crush of gravity due to electron degeneracy pressure. Now because of the nature of degenerate matter, as the white dwarf's mass increases, the radius of the star actually shrinks. And this is because electron degeneracy pressure always pushes out with the same amount of force. So we have the same amount pushing in, but as we increase gravity, the crush of gravity is going to get greater, which means that the star is going to have to shrink some. Now, we can see this by looking at this graph. So up and down, we have the radius of the white dwarf. And then along the bottom, we're looking at the mass of the white dwarf. Okay, so right here, we're looking at a white dwarf with 40% the mass of the sun. At 40% of the mass of the sun, it is larger than the Earth. At about 80% the mass of the sun, it's about the size of the Earth. Then at 1.2 solar masses, it's smaller than the Earth, going to be closer in size to something like Mars. Electron degeneracy pressure can actually only support so much gravity. This is something that we touched on previously when talking about the core collapse leading to a supernova explosion. So for a white dwarf, the composition being mostly carbon and oxygen, this limit is at 1.4 solar mass. You can actually see this on the graph that at 1.4 solar mass, the radius goes to 0, which is kind of weird. But at 1.4 solar mass, gravity beats electron degeneracy pressure, so we have this limit. This is sometimes referred to as the white dwarf limit, also called the Chandrasekhar limit, named after the Indian astrophysicist who figured all of this stuff out in the 1930s. So we do not find any white dwarfs greater than 1.4 solar mass, because at that point, gravity beats electron degeneracy pressure. Now, when we first see the white dwarf, when the outer layers have finally blown off and the white dwarf is revealed, it's still going to be really, really hot. However, as it cools, electromagnetic interactions are going to be able to overcome, causing the white dwarf to begin to crystallize. Now, as it crystallizes, the type of crystal, of carbon crystal that can survive at these pressures and temperatures is actually diamond. What this means is that a white dwarf is actually a diamond the size of the Earth, which is pretty awesome. Now, we talked about this idea of mass transfer before. It's not just going to be mass transfer between giants and main sequence stars. We could also have mass transfer from a giant onto some sort of stellar remnant, in this case a white dwarf. As this happens, it can lead to what we refer to as a nova. So we've talked about supernovas before. That's where the entire star explodes. This is just a nova. Okay, so notice we're not calling it super, so it's going to be smaller, but it's still relatively interesting. So the idea is that we have an evolved companion losing mass onto the white dwarf. As this happens, it's going to be predominantly hydrogen, so we get this layer of hydrogen building up on the surface of the white dwarf. As it continues to fall, that hydrogen envelope, the hydrogen layer surrounding the white dwarf, is going to continue to compress and heat up. At some point, it's going to compress and heat up enough that we'll get a sudden burst of hydrogen fusion in that hydrogen envelope. Okay, so we get this burst of hydrogen fusion. What this is going to do is it will cause the star to suddenly become brighter than it was normally. So in this graph, we're looking at a light curve. Up and down, we're looking at the apparent magnitude. And then along the bottom, we're looking at time. So this star starts out with an apparent magnitude of around a +8. So can we see this star at the very beginning? No, we can't. The visual limit is at a +6, and remember, magnitude is backwards. The greater the magnitude, the fainter the star is. So if the number is greater than a +6, we can't actually see the star with our naked eye. So it starts out, we can't see it. Then we get that burst of hydrogen fusion, and the star suddenly becomes brighter, jumping up to somewhere around a +2. At a +2, this is easily visible. So we went from a region that appeared to have no star, and then all of a sudden we have a star, and it's going to take a little while before a few days or a couple of weeks until it finally fades out so we no longer see it anymore. So we have this thing where a star suddenly appeared. In fact, the term nova actually comes from the ancient terms for new star. Now, the white dwarf itself is still going to be around after this happens, which means that it's possible for the same star to nova repeatedly. One example of this is the star RS Ophiuchi. This is in the constellation Ophiuchus, which is near this constellation Scorpius. This has erupted in 1898, 1933, 1958, 1967, 1985, and also 2006. Now, unfortunately, it's not on a regular pattern, so we can't say exactly when it's going to erupt again, but it's pretty awesome that we can say that it will erupt again. Here is our fourth lecture quiz question. What happens during a Type 2, 1b, and 1c supernova? A. The start of hydrogen fusion in the core. B. The start of helium fusion in the core. C. The end of fusion and core collapse. Or D. The end of fusion and a mild dispersion of the atmosphere. Go ahead and think about it, and we'll discuss in just a bit. Alright, so what happens during a supernova? Or at least these three types. It is C, the end of fusion and core collapse. Now, we mentioned that there were four types. Type 2, 1b, and 1c are all core collapse of a giant, some kind of supergiant. But Type 1a is a completely different mechanism. In this case, what's happening for a Type 1a supernova is that we have a white dwarf that is gaining mass from a companion. Now, once that white dwarf has gained enough mass from its companion, then it can get pushed over that Chandrasekhar limit, that 1.4 solar mass. Once it's above 1.4 solar mass, then gravity beats and it suddenly collapses. Now, as it collapses, it's going to heat up with greater pressure, and that means that it's going to actually get hot enough with enough pressure to suddenly begin carbon fusion. So as it shrinks, it begins carbon fusion, but it has now lost all of the outer layers of the star, which we're adding pressure and gravity to help that core stay the same size. Without those outer layers, that fusion pressure is going to overcome gravity, and the star will then explode. Okay, so this is what happens during a Type 1a supernova. A white dwarf gets pushed over the limit and explodes. Okay, in this case, 100% of the star is going to be lost to space. In other words, a Type 1a supernova happens exactly one time and after that, the star is gone. It will never happen again.